Okay, so now what we want to do is we want to determine the structure of a voltaic cell and also determine the cell potential. We have looked at how to make, actually the difference between a spontaneous and a non-spontaneous reaction. So we want to combine this with making a spontaneous reaction so that we can actually have a voltaic cell or a battery. And a couple points here, a voltaic cell is an electrochemical cell that happens spontaneously, so that's pretty important that it happens spontaneously. And in the process, it's going to produce a voltage. So that's something that we see. We'll always know what the voltage is. And a common name for a voltaic cell is a battery. You should know that. And another term, we've already talked about electromotive forces, and we've also already talked about the fact that all of this stuff happens at standard conditions. So you can look at the top of your reduction potential tables and you can see these standard conditions of 1 molar, 1 atmosphere, temperature of 298 Kelvin. So now, in order to determine the potential of that cell, what we need to do is we need to we're given an example here where we're asked what the voltage would be of a voltaic cell that is prepared with copper metal, 1 molar solution of copper 2 nitrate, iron metal, and iron 3 nitrate. Again, that would be a 1 molar solution of iron 3 nitrate. So the first thing you could look at here is you could think about your half reactions because we've done this. Now keep in mind, I know that we've got compounds, we've got copper 2 nitrate and we've got iron 3 nitrate, but we know that the nitrate is just a spectator ion. It goes away. So really what that tells us is that we've got copper 2 ions and we've got iron 3 ions. We don't need to worry about the spectator ion of nitrate. So our first step is to write the two half reactions showing the metal ion being reduced. So that's the big important thing here. We've got our two half reactions. We don't know which ones the oxidation is occurring. We don't know where reduction is occurring. So we have to show them both as half reactions as reduction halves. So when we write that down, the first thing we'll write down is, I see we've got our copper plus 2 going to copper, and we've got our iron plus 3 going to iron. And again, I did this as a reduction half. In other words, in both of these reactions, we are gaining electrons. So we did this so that we could very easily look at our reduction potential tables and determine the charges of these, the voltages. And when we look, we see that the voltage for our copper for this reduction half reaction is going to be 0.34 volts. And for our iron, it is going to be a negative 0.04 volts. But wait a minute, it's not possible to have two half reactions that are both reduction halves. So what we now need to do is step 2, reverse the direction of the more negative half reaction. Because we know that we're trying to create a battery. So what we want is we want our cell potential to be a positive value. We want this to be a battery. We want it to be a spontaneous reaction. So we need to switch the more negative half. And for that, we come across the fact that it would be our iron that is going to need to be switched. So I'm going to rewrite that. And instead of it being a reduction half, it's going to be an oxidation half. It is going to be iron turning into iron plus 3 electrons. Now, instead of being a negative 0.04, it's going to be a positive 0.04 volts. And I'm going to continue writing my other half reaction just the way I saw it, my copper half reaction, with the 2 electrons added to the left side as a reduction. And that stays the same as a positive 0.34 volts. So now when I add this up, I see that my value adds up to a positive value, and that positive value is a positive 0.38 volts. So we have created a spontaneous reaction. We purposely did that. We made it a positive value so that this battery would work, so that it would be a voltaic cell for us. Now what we want to do is we want to go ahead and make the number of electrons transferred equal, because I see that we've got 3 in our iron half reaction and 2 in our copper, so we need those to be equal. So we know in this first one we're going to have to multiply it times 3, and in the second one we're going to have to multiply it times, I think I said that wrong. First one's multiplied times 2, the second one's going to be multiplied times 3. So we're going to get them to be equal to 6 electrons so that that'll cancel out. So when we do the math, we get 2Fe yields 2Fe plus 3 plus 6 electrons. And we also get 6 electrons plus 3 coppers yields 3 copper ions. And then that's going to yield 3 copper atoms on the right side. So that's written correctly now. And we did that so that our 6 electrons would cancel out. And now we can even write an overall reaction from that. So step 3 is asking us to make the number of electrons transferred equal and then add the 2 half reactions. Because what this does is this is going to give us our overall balanced reaction right down here. And that answer is going to be 2Fe plus 3Cu plus 2 yields 2Fe plus 3 plus 3Cu. So there's our overall balanced reaction. Something I want to go ahead and make a note of right now while I'm thinking about it is in step 2 here, I see that I've lost my electrons in this half reaction, so that's got to be my oxidation half. Here I see with my copper I've gained my electrons in this half, so that's got to be a reduction half. That's going to be helpful for me when I'm actually drawing my voltaic cell. I think right now, though, I'm going to skip the drawing. That'll be in the next video. And I'm going to go ahead and jump down to how we can do a shorthand notation. Because what we've just done, let me go ahead and highlight this, that this right here is our overall balanced reaction. That is a long way to write that, but it shows what's going on. And we know what we're starting with is solid iron and copper ions, and we're going to end up with iron ions and solid copper. Well, another way that we could write that, it says what would be the shorthand notation to describe the cell. And bear with me as I rewrite this really quickly. So we've got this, I believe this is right. This was our overall reaction that we had that's balanced. We could write it this way, that's pretty long, or we could write it a shorthand notation. And a way that you can remember that is that you can write it the long way, or you can write it the shorthand way. And think about this as being oxidation first, and then reduction is what you're going to be writing there. So the trick is for these, you write the oxidation half first. And remember, if we go back here, we saw that our iron was being oxidized. Right there is where we see our iron is oxidized. Our copper is reduced. So we're going to do our oxidation half first, which is our iron. And I see that my iron, I start off as a metal, then I go to my ion. So that's what I'm going to write, my oxidation half, where I've got iron going to iron ions. That's the oxidation half. Then I do a double slash, and I do my reduction half. And my reduction half, remember, is going to be the copper. So when I look at my balanced overall reaction, I see that I've got my copper ions going to solid copper. So copper ions yielding solid copper. So that would be how you write the shorthand notation for this cell. The top one I've got here is the overall reaction, that's long method, and then we have our shorthand notation. And then the last little bit here, it says if you know that copper 2 has a blue color and iron 3 has an orange color, predict what will happen to the colors of the cells as the reaction goes by. Well, it only makes sense. Let's see, I should do this in the right colors. We know that copper 2 is blue. Those ions, when it's in solution, it's blue. And we know that iron ions are going to be orange. So that's what we end up seeing when it's in solution. So over time, we see that the copper is going to go away and the iron 3 is going to increase or appear. So the way we could write that is we could just say that the blue disappears and the orange appears, or you could say it increases, something like that. And that should do it. I will work with voltaic cells on the next video.